Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 6 from the October-November 2001 Mechanics M1. This is from the 9709 syllabus, except this is such a long time ago. It was called 8709 in those days. So anyway, this is a question about pulleys, okay, which is still relevant to our syllabus today. And I've chosen this question because I set this question in one of my tests. And the last part of the question, quite a few students got that part wrong. So I'm going to go through this question to make sure that everyone understands what's happening. So that's the reason why I've chosen this question. I know it's a very old one, but old is gold, as they say. Anyway, so particle P has a mass of 0.4 kilograms and particle Q has a mass of 0.5 kilograms. They are attached to the ends of a long, light and extensible string which passes over a smooth pulley. The system is released from rest with both particles at a height of 4.5 meters above the ground. As shown here, the particles move vertically and Q does not rebound when it hits the ground. So when they start moving, Q is going to move downwards and P is going to move upwards. They're going to both be accelerating with the same acceleration because they are both attached to the same inextensible string. So inextensible means any particle, it doesn't like stretch. So any particle attached to it when it is tight, okay, or taut as they say, when there's tension in the string, any particles attached to it will have the same acceleration. Okay, so we got to find the acceleration of Q before it hits the ground. So the acceleration of Q while it's falling, basically. All right. So what we're going to do is I'm going to draw a little diagram to show the forces acting on P and on Q. So P has a mass of 0.4 kilograms. Okay, this is P. And Q has a mass of 0.5 kilograms. So the forces acting on them are going to be their weights. So you have the weight acting on P vertically downwards. And you have also the tension of the string, which is, acting upwards. And you have for Q as well, the weight and also the tension in the string, which is acting upwards. Okay, so you have the tension and the weight. The weight is 0.4 times G. And here the tension and 0.4 times G. So the tension in both strings is also the same because of two reasons. One, it is a light string, so that means we don't consider its weight. So the tension throughout the string is the same. The bottom part of the string is not holding more weight than the top part. If it was not light, then that would be the case, and the tension on the bottom would be more than the top. But because it's a light string, means we're ignoring its weight the whole way. We're ignoring the weight, so the tension is the same all the way through the string. And the other reason why the tension on both sides of the pulley are the same is because it's a smooth pulley. Okay, so there's some modeling assumptions that I think in EdXL they're more relevant. They normally ask about those assumptions. In Cambridge, I haven't really seen questions asking about those assumptions, but it's good for us to understand why they give us these terms. Anyway, so those are the forces acting. Now, as we said, Q is accelerating towards the ground with the same acceleration that P is accelerating upwards, same magnitude. Okay, so what we're going to do is we're going to consider P and Q separately. So I'm going to consider P separate to Q. So if I consider P, now as P is moving upwards, I'm going to take up as positive for P. And if I take up as positive for P, I'm going to look at the resultant force acting on P. It's accelerating, so I know that the resultant force is equal to the mass times the acceleration. So the resultant force here on P, if we take up as positive, is T minus 0.4 G. So T minus 0.4 G is the resultant force, and that's equal to its mass, which is 0.4 times its acceleration, which we don't know, and that's what we have to find. So here we have two things that we don't know, the tension and the acceleration. And if we look at Q, similarly, we can do a similar thing, but Q is moving down. Q is accelerating towards the ground. So for Q, I'm going to take down as positive. Q, I'm going to take down as positive, in which case I'm going to have 0.4 G minus T equals a mass times acceleration. So 0.5 G, sorry, what am I doing? 0.5. I was about to make a silly mistake there. That's 0.5 G. Because its mass is 0.5, its weight is 0.5 G. So 0.5 G minus T equals its mass 0.5 times its acceleration. So here we have two equations, equation 1 and equation 2, which we can solve simultaneously by adding them together. Okay, if I add these two equations together, I have, these t's with opposite signs that will cancel out. So if I add these two equations, I'll have t minus t, which is 0, have minus 0.4g plus 0.5g, which is 0.1g, equals, and if I add these together, I'm going to get 0.9a. So if I divide both sides by 0.9, I'm left with 0.1g over 0.9 equals a. You can say a is equal to 1 over 9 g meters per second squared. Okay, now if you want to leave it like this, that's fine. Okay, in fact, I can leave it as g over 9, probably better for now. So g over 9 meters per second squared. However, we should really put it to 3SF. Most mark schemes will show that. Now, this is where Edexcel and Cambridge will be different. In Cambridge, you would use g as 9. So you end up with 10 over 9, which gives you 1 and 1/9, which is 1.11 recurring. So we can just write 1.11 to 3SF meters per second squared. And there's your answer. The answer for this question, according to this board, is 1.11. If you were going to use Edexcel, you would say 9.8 over 9. And then you'd give your answer to 3SF or 2SF if you wanted to. And that would be your answer, slightly different. You could even leave it in terms of g if you want. G over 9 and 1 over 9g. That's normally fine as well. All right, so there's part 1. Now for part 2. It says the time taken from the instant that Q hits the ground until P reaches its maximum height. So what's going to happen here? Q is going to hit the ground. When Q hits the ground, okay, so of course Q is going to fall through 4.5 meters. Now P is going to rise up 4.5 meters. Okay, so it's going to rise up to this level over here. Okay, this line was from previous messing around I was doing. So that distance that it moves up, okay, is going to be how high it moves while Q is falling. Okay, so that's all right. So, but we're concerned about what happens after this. So it's risen this 4.5 meters, and then after this, what's going to happen is once Q has hit the ground, the string will have normal tension. So when Q hits the ground, P will be up here, and the string will have normal tension. So if you think about P, what's going to happen to P? You're going to have just the weight acting on it, nothing else. It will only be the weight acting on P, which will be straight down. So this is P once Q has hit the ground, and the weight of this is 0.4 G, and the tension in the string is gone. The tension in the string is no more because Q has hit the ground and the string is now taut. It's not taut, it's basically slack now, so there's no tension in it. So what's happening to P? The force acting on it is accelerating towards the ground with magnitude G acceleration, because the only thing acting on it is its weight. All right, so it's obviously going to reach a maximum height. Okay, so it's going to go up for a little bit now, and then it's going to come to rest. So I'm going to call this point A, and this level B. So A is the point that it reaches once Q has hit the ground, and B is how high it reaches as it's rising only due to the force of gravity, no tension in the string. Okay, so I'm going from A to B. Now, what direction is P moving on in at A? It's moving upwards. So I'm going to take up as positive. Okay, and so what is the resultant force acting on P? The resultant force is only acting downwards. Okay, so you can say the resultant force here is minus 0.4 G, okay, is equal to its mass, which is 0.4, times the acceleration, which is A. Okay, so basically it's just going to be minus G. We don't even have to do that. Okay, I don't even know why I did that. We know it's minus G. Why are we saying minus G? Because it's going up and it's going to go down. So we don't need to even do that because we know the only force acting on it is G, but you see how that works anyway. So what we're going to do is we're going to use Suvat. Okay, Suvat is going with a constant acceleration of G towards the ground. Now we're taking up as positive and G is acting down, so we're going to put minus G. Okay, S we don't know. T we have to find. Okay, V is going to be 0 because of course it's going to rise and comes to instantaneous rest. It reaches its maximum height when it comes to rest before it falls down again. It's going to fall down again, right? It's going to rise, and then the only force acting is gravity, and it will stop. It won't continue. It will carry on until there. Then it will fall down again. So we can say that v is 0. So we have v, we have a. We need to find t, and which of these will help us? Well, if we can find u, which was its speed, okay, at the same time when q hit the ground, we can then solve this problem. So basically, the speed that this is going at as q hits the ground is going to be the same speed as q is going at, right? When it hits the ground. At the point when q hits the ground, these two will be moving at the same speed. Just as this is hitting the ground, that will be rising at the same speed because they're connected by a light string, so an inextensible string. So what we can say is, let's go back to q. Let's see what's happening with q as it's falling and see what its speed was when it hit the ground, which is this. Okay, now the initial velocity of q is 0 because the whole system, as it says here, was released from rest. Okay, the distance through which it's fallen is 4.5 meters. And remember, for q, we were taking down as positive as it was falling down. So s is 4.5 positive because it's taking down as positive. A is going to be acting downwards, and acceleration was what we found. The acceleration before q hit the ground was due to the tension and the gravity. So it was the acceleration we found over here, which was 1 over 9g, 10 over, let's call it 1 over 9g. Okay, this is v, this is 1 over 9g. And the time we don't know. So we can use here v squared equals u squared plus 2as. So you have v squared equals u squared, which is 0 squared, plus 2 times 1 over 9 times g times 4.5. So what do we end up with? V squared equals, this will be 2 times 4.5 is 9, divided by 9 is 1. So we're left with 2g, just g. V squared equals g. So I'm going to write v is equal to the square root of g. Okay, so v is equal to the square root of g. In fact, I think I'll be able to use this. Okay, square root of g. So if we work that out, we're going to have 9.8, square root of 9.8. If we're going to be doing, or square root of 10, sorry, square root of 10 for Cambridge. Square root of 10, not 9.8. Okay, which is going to give you that 3.16. I'll leave it as root 10. So v is equal to root 10 for us now. V is equal to the square root of 10 meters per second. Okay, so that is going to be the u here, square root of 10 meters per second, and it's going to be going upwards, so it's going to be negative. Okay, in this case, it's going to be negative. We're taking up as positive. We're taking up as positive. No, actually, we're taking up as positive, yeah, and u is going to also be positive, sorry, because it's moving upwards. P, the beginning is moving upwards, and it becomes 0 at the top. So it's going to be positive, sorry about that. So we can say now v equals u plus at in this situation between a and b. Now we know v is 0. We know u is going to be the square root of 10 plus a, which is minus g times t. So we can find what t is. You're going to have g times t equals root 10. So t is equal to root 10 over g. So it's going to be root 10 over 10. Okay, which will give us our answer. Okay, so we have root 10 over 10. If we put that into our calculator, we have the square root of 10, over 10. That gives us 0.31622. What happened there? 0.31622. So the time to 3SF is 0.316 seconds. There's the answer. Okay, to part 2. All right, so we need to find the velocity of q as it hit the ground, which was the velocity of p when it reached its height, 4.5 meters above where it started when the string became loose. And then we needed to use suvat with g as the only acceleration acting downwards, taken up as positive because, why? Because it's moving up at that point that we called A. It's moving upwards. Initially, it's moving upwards. Take upwards positive. So we have S. We don't know. U is root 10. V is 0. How do we find root 10? We found it by using suvat for Q as it hit the ground. Find the speed of what it was. A is minus G because we're taking upwards positive, it's acting downwards. And we can therefore find what we need, the time it taken, by rearranging this equation. Okay, so the time taken from the instant that Q hits the ground until P reaches its maximum height. There's the answer to part 2. Right now, the next part of the question says the total distance traveled by P while Q remains at rest on the ground. Okay, so now what's going to happen is P, as we said, is going to rise, and we found it up to now the point B. Now what's going to happen is going to go from B back to A again. Okay, it's going to go from B back to A. Okay, now when it goes back to A, that's when the string is going to become tight again, and then there will be tension in the string, and then Q might start to move. Right? So we want to find the total distance it's moved. Okay, it says the total distance traveled by P, okay, while Q remains at rest. So you got to find the total distance between A and B, and then back from B to A. And this is where people make mistakes. They just found the distance from A to B, from the distance to the highest point. They didn't double it. What we got to do is double that, right? So I've got to take the same situation that I have here, but find the time. Same information as here, but find how long it takes for it to get to B. Okay, so I need the same information that I've got here. So I'm going to take that information and put it on the next page. Okay, so let me just take this information. Okay, so now I need to find what S is. So we can use V squared equals U squared plus 2AS. I could also use the T that I found, but I think this is going to give us a better answer. V squared equals U squared plus 2AS. So V squared is 0. U squared is going to be 10 plus 2 times minus G times S. Okay, so you have 0 equals 10. Now, if we take that minus 20 as minus 10, so you're going to have minus 20s. So you have 20s is equal to 10. So s is equal to 10 divided by 20, which is 0.5 meters. So from A to B, if we go back here, A to B means, okay, from the point where the string became light to the point where it reached its highest point, P reaches its highest point, and then we need to also find, so that's 0.5 meters, so it's gone 0.5 meters up, and then 0.5 meters down until it reaches this level again. Once it reaches this level, the string will become tight again, and Q will start to move. All right, so we've got to take this distance S, and we've got to think about going up, and then coming down again. So 0.5 meters up, 0.5 meters down. So we can say that the total distance traveled by Q while P remains at rest on the ground, we can say the total distance is equal to 2 times 0.5 meters, which is 1 meters. Now, those of you who did everything right in the question, I think there's only one student who actually multiplied the answer by 2 at the end. Okay, most of the students gave 0.5 meters as the answer. That's what you normally find in the questions. You have to read the question very carefully here. What the total distance traveled by P. Some people just finish reading there. They think, oh, I know what the question is asking. You know, it's like, how high did P go after Q remained at rest on the ground? No, basically, what you have to do is find the distance that P went up, came to instantaneous rest, and then came down again. All right? And then once it comes down to that same level where the string becomes tight again, that's when Q will start moving. So Q won't be at rest anymore. Okay, so the answer here is 1 meter. So take care of that. Read the questions carefully. Anyway, that concludes this question from the October-November 2001 paper, Mechanics 1. Other questions from this particular paper, if I get to answer them, will be in the playlist that will appear in this region over here. Other questions from the topic of constant acceleration, okay, you'll find them in this playlist over here. Connected particles will be maybe another playlist that I make, which I will make and put questions dealing with connected particles, pulleys, and these kind of things in the playlist over here. You can subscribe to my channel by clicking on this link, and you can find the material I have made for Cambridge and Edexcel and IGCSE and different things. If you watch the video, the card will appear at the top of this video a few times during the video, and you can click on that card. It will take you to another video which explains how to use my channel. Thank you for watching, and see you soon.